Good morning, everyone.
I am Alejandro Díaz-Caro.
And I am Gilles Dowek. First, we want to apologize. We would have been delighted to be with you in Haifa this morning, but we could not make it. And we want to thank the organizers for giving us the opportunity to talk to you through this video. The title of our talk is Linear-Lambda Calculus is Linear, and we all know there is a link between linear logic and the algebraic notion of linearity. In particular, a proof of a linear implication between two propositions A and B should not be any function mapping proofs of A to proofs of B, but it should be a linear one. This idea has been fruitfully exploited to build models of linear logic, but it has been much less exploited in the syntax in the proof language of linear logic. Indeed, if we want to express a property such as f of u plus v is equal to f of u plus f of v, we need to have a symbol plus in the proof language, and usually we don't have one. This situation has changed with the invention of quantum programming languages, where we are used to mix programming language constructions, such as abstraction, application, and so on, with algebraic operations, such as addition and multiplication by a scalar. In this talk, we want to introduce an extension of linear logic with two new deduction rules, one for addition and the other for multiplication. And this will lead to have two new operations in the proof language. And we want to prove a linearity theorem. If f is a proof of an implication between two propositions of some specific form, then f verifies these two linearity properties. F of u plus v is equal to f of u plus f of v, and f of a times u is equal to a times f of u. These algebraic operations are introduced in two steps. The first one is to extend linear logic with two new interstitial rules. So what is an interstitial rule? It is a deduction rule whose premises are exactly copies of its conclusion. So we have here a binary interstitial rule, the sum rule, and a unary one, the prod rule. Of course, these two rules do not extend the set of provable sequence, but they introduce in the proof language two new symbols, plus and times. And the fact that these rules are trivial is an expression of the fact that these operations, plus and times, are internal operations. These rules enable to build a proof such as this one, where a conjunction is first introduced and then eliminated, but where a sum rule has been inserted in the interstice between the introduction rules and the elimination rule. And if we want to reduce such a commuting cut, we have first to commute the sum rule either with the elimination rule below or with the introduction rules above. And in this work, we have decided to commute as much as possible the interstitial rules with the introduction rules, rather than with the elimination rules. That is, we commute the interstitial rules with all introduction rules except those of the disjunction, and we commute the interstitial rules with the elimination rule of the disjunction. And this choice leads to a stronger introduction property for normal proofs. Once we have introduced these two interstitial rules, we can proceed to the second step, which is the introduction of scalars. To do so, we have to choose a field of scalars, and usually we choose either the field of real numbers or that of complex numbers. And then we replace the introduction rule of the true symbol with a family of rules, one for each scalar. And in the same way, we replace the prod rule that we have just introduced with a family of rules, one for each scalar. To conclude the design of our logic, we have to make a choice of the linear connectives we include in it. In intuitionistic linear logic, there is no multiplicative falsehood, no additive implication, and no multiplicative disjunction. So we don't really have a choice for falsehood, implication, and disjunction. We do have a choice for truth and for conjunction, and we have decided to take the multiplicative truth and the additive conjunction. We could also have added the additive truth, but this was not useful in this logic. But we could not have taken the multiplicative conjunction if we want to commute the interstitial rules with the introduction rule of the conjunction. So this leads to this choice. We have a multiplicative truth, an additive falsehood, a multiplicative implication, an additive conjunction, and an additive disjunction. And you can also notice that the sum rule is additive. These connectives are often written with a typical notation of linear logic. In this talk and in our paper, we have chosen to use the more usual notations for truth, falsehood, implication, conjunction, and disjunction. But of course, this is just a matter of choice of notations, and if you don't like our notations, you can use others. This discussion leads to the following deduction rules, and you can notice that most of these rules are just the usual ones. For instance, you can see here the rules of the conjunction that are the usual ones, except that we use an extended elimination. Then we have the two interstitial rules, the sum rule and the product rule. And you see that we have just introduced a notation for the proof T plus U formed by aggregating a proof T and a proof U of the same proposition in the same context with the sum rule. And for the prod rule, we have the multiplication, and as we have one rule for each scalar, the proof term is the multiplication of the term T with the scalar A. In the same way, instead of having a single proof of the true proposition that would be written star, we have one for each scalar, and we write this proof A dot star. Finally, in linear logic in general, we have an elimination rule for the true proposition, which is slightly unusual if you think of intuitionistic natural deduction, for instance. And here, in this rule, we have a proof T of the true proposition and a proof U of proposition A. And we build the proof elim top of T and U, which is another proof of A. But just notice that this proof is in the context gamma delta instead of being in the context delta alone. We can now discuss the reduction rules of this calculus. And again, you can notice that most of these rules are the usual ones. For instance, you have here the beta reduction rule. For the cut, which is created by an introduction rule of the true connective followed by an elimination rule of this same connective, if we didn't have any scalars, the rule would be elim top of star and T reduces to T. But here we don't want to drop the scalar A, so we multiply on the right-hand side the proof T with this scalar A. Then we have examples of commutation rules. So for instance, this is the commutation rule between the sum rule and the introduction rule of the conjunction. And there is an exception, which is the commutation of the sum rule with the elimination rule of the disjunction, because we cannot commute it with the introduction rule of the disjunction. Then we have the two interesting rules in this calculus. So when we commute the sum rule with the introduction rule of the true connective, if we didn't have any scalars, we would have a rule of the form star plus star reduces to star. But here we have scalars in the three proofs stars. So on the left-hand side, we have a proof A star and a proof B star, and we make the decision to take on the right-hand side the proof A plus B star, where the two scalars A and B have been added with the addition of the field. And in the same way, when we commute the prod rule with the introduction rule of the connective true, then we get a proof which is of the form A times B star, and we decide to reduce this proof to A times B star, where the two scalars A and B have been multiplied using the multiplication of the field. This calculus is confluent and it terminates, and the closed irreducible proofs in this calculus have a strong introduction property. They always end with an introduction rule, except those of a disjunction that are linear combinations of proofs ending with an introduction rule. The subject reduction property can also be proved by the proof is slightly more subtle, as this is the point where we have to exclude multiplicative conjunction. Indeed, if we had a commutation rule such as this one, a commutation rule between the sum rule and the introduction rule of the conjunction, if the conjunction were multiplicative, this rule would not enjoy the subject reduction property, and this is why we have to choose the additive conjunction. Now we can see that this calculus is indeed a good calculus to speak about vectors and linear maps. So first we can remark that by constructions, the closed irreducible proofs of the true proposition are in one-to-one correspondence with the elements of S, the scalars. And we can deduce that the closed irreducible proofs of true and true are in one-to-one correspondence with the elements of S square. And in the same way that the closed irreducible proofs of true and true and true are in one-to-one correspondence with the elements of S3. This leads to introduce a set V of propositions called the vector propositions, which is the smallest set containing the true proposition and closed by conjunction. Then, if we consider an arbitrary vector space of finite dimension n, then it is well known that this space is isomorphic to S to the n, hence it is in one-to-one correspondence with the set of closed irreducible proofs of any vector proposition A with n occurrences of the true connective. So each proof corresponds to a vector, and each vector corresponds to a proof. And of course, this correspondence, just like matrices, is basis dependent. Moreover, the sum of proofs that has been introduced with the sum rule in the logic corresponds to the sum of vectors, and the product of a proof by a scalar corresponds to the product of a vector by a scalar. If you look again at this reduction rule that has been introduced as a commutation rule between the sum rule and the introduction rule of the conjunction, and remember that this commutation rule was needed in order to reduce the commuting cuts, then we can see that this rule is also a vector calculation rule that adds the coordinates one by one. Once we have represented the vectors, we can represent the linear maps in the calculus. So if A and B are two vector propositions of dimension m and n, that is with m occurrences of the true connective in A and n occurrences of this connective in B, and M is a matrix with m columns and n lines, then we can build a closed proof T of the proposition A implies B that corresponds to the matrix M. That is, if we apply this term T to a term representing a vector U, then we obtain a term that represents the vector mu. This proof is not too difficult. It is a simple induction on the structure of A, or if you prefer, on the natural number M, and it proceeds by decomposing the matrix into blocks of columns. So for instance, if you consider the 2 by 2 matrix A, B, C, D, it is expressed as the term that you can read on this slide. And if you apply this term to the vector EF, then you get a vector which is the vector you expect from the matrix multiplication. So we are now ready to express the main theorem of our paper, which is the converse of this property. That is that if you take a proposition A, an arbitrary proposition A, and a vector proposition B, and a closed proof T of the proposition A implies B, then this proof T expresses a linear map in the sense that if you apply this proof T to a proof of the form U1 plus U2, then you get a proof which is convertible with the proof TU1 plus TU2. And in the same way, if you apply this proof T to a proof of the form A times U1, then you get a proof which is convertible with the proof A times TU1. The proof of this theorem is more difficult. It uses well-known techniques and also new ones, and I'm afraid that if you want to understand the details, you have to read the paper. The paper also contains more motivations for this calculus, and in particular applications to quantum computing, which is where we come from. Future work includes relaxing the condition in the statement of the main theorem that B has to be a vector proposition, and relaxing this condition would yield a higher order vector calculus. We are now ready to take questions. Thank you.